In this lesson, we're going to look at the vertex form of a quadratic function. Now, before I go through and explain it, I'd like you to go through and do this investigation. The investigation is going to ask you to change the coefficient of x squared. It's going to ask you to change the constant at the end, and then it's also going to change the constant within the set of brackets. So go ahead and try that out. Hit pause on the video, and once you've done that, come back and we'll have a look and see what all of these different values mean and how that affects our vertex form of the equation. Okay, so now that you've done that, what does changing that coefficient do? Well, it's the same thing as what happened when we changed the coefficient and we looked at the standard form of the quadratic function. Changing that coefficient to a value greater than 1, because our parent function has a value of 1 there, that made our graph narrower, but it didn't change the vertex and it didn't change the axis of symmetry. When I changed it to a value less than 1, it made my quadratic function, my parabola, wider, but again, it didn't change my vertex and didn't change my equation for my axis of symmetry. Now in B, we're asked to change this constant. The constant is tacked on to the end of our parent function, y equals x squared. We know what that shape is. It's the one I graphed in the middle up here. But what does adding a constant to the end do? Well, I graphed the one with plus 1 and I noticed that my vertex was moved up to 0, 1. But everything else stayed the same. The width stayed the same, right? Then I tried, okay, let's try a different value. I tried plus 4. Same thing happened. Instead of moving up 1, it moved up 4 spots. So my vertex is now at 0, 4. So trying a negative 1, I thought, well, what would that do? And sure enough, it bumped my graph down to negative 6. I need a negative in there. Bumped it down to negative 6 on the y-axis. So all it was doing was moving my graph up and down, but the width stayed the same. Now, for C, this looked a little different. The value that we were changing is within the set of brackets. Now changing that value, what did that do? That was very much like what we did with the factored form when we only had one factor. And if you look at our graphs, one factor means one root, right? So x minus 3, right in the middle here, that put my vertex at positive 3. X minus 1, that put my vertex at 1. X plus 2 put my vertex at negative 2. So it's shifting my parabola left and right. The width stays the same, but it's moving opposite what you would think it would be. This first one, I thought it would move minus 1, so I thought it would move in the negative direction, and in fact it moved in the positive. So it's moving opposite the way that you would intuitively think it should go. And that's related to our factored form, right? When we had our factored form, we had x minus s and x minus r. But that was built into our equation, right? So the value of r and value of s were our factors, were our roots, and that's where they came out of. X minus r and x minus s were our factors, r and s were my roots. Okay, let's talk a little bit about this on the next page, put this all together. So the vertex form of the equation of a quadratic function is written as follows. We have y, which now you know is interchangeable with f of x, is equal to a. That's still the same a value that affects our graphs, but now x minus h squared plus k. Now it says here the graph of the function can be sketched more easily using this form. Let's have a look at what they mean. A quadratic function that is written in vertex form has the following characteristics. The vertex has the coordinates h, k. So let's look where that is. So h is here, k is here. So you could pick your vertex out right away. The equation of the axis of symmetry of the parabola is x equals h. Well, that makes sense because we always look at the x value of our vertex to figure that out. So those values are the same values. That's good. The parabola opens upward when a is greater than 0, and the function has a minimum value of k when x is equal to h. So the parabola opens upward when a is greater than 0 means that a is positive. So we know that when a is positive, we have a minimum. When a is negative, we have a maximum. And that isn't any different than our other formats. That still holds true. But what's this other part? The function has a minimum value of k when x is equal to h. Well, that would be h minus h. So that would be 0. So k would actually be your minimum value or maximum value when x is equal to h when a is negative. All right, so if we look at our graphs here, they've actually drawn that out for us, which is really nice to see. We've got our vertex here at hk, right? When x is equal to h, you can get your minimum or your maximum out, and your axis of symmetry is going through that h value. The rules don't change in terms of how many zeros we have, how many x-intercepts, how many roots. They can have 0, 1, or 2 depending on the location of the vertex and the direction in which the parabola opens. By examining the vertex form of the quadratic function, it's possible to determine the number of zeros and therefore the number of x-intercepts. So we can look at these equations and get everything out of there actually without having to go too much further. Okay? And then you have this, I think, at the bottom of your page there. So the 2 x-intercepts, 1 x-intercept, and no x-intercepts. And what we're talking about are these roots here. And here it doesn't, the last one doesn't cross at all. Let's try a couple of examples out and see where this is all heading. So if we look at this first one, it says predict, meaning don't put it in your calculator yet, what these functions should look like and sketch the graph without using a graphing calculator. All right, so x squared plus 3. Now, remember the vertex form of our quadratic function here, y equals a, and then we've got x minus h squared plus k. Okay, so in this case, if I were to rewrite the first one, y is equal to 1, it would be x minus 0 squared plus 3. Because I've got an a value of 1, I don't have an h value in there, and I've got a plus 3 at the end. So if I'm looking at my vertex and I'm finding my h and my k out of there, my h value would be 0, and my k value would be 3. Axis of symmetry then would be 0. My y-intercept, how do I figure that one out? Well, you would plug in x is equal to 0, and if we plug in y is equal to 0 squared plus 3, that would just give me a y-intercept of 3. How many zeros does this have? How many times does it cross the x-axis? Well, let's go ahead and sketch this so we can see how many zeros we have. So if the vertex is at 0 and 3, and we know that the a value is positive and it's opening up, well, if it's opening up and the vertex is there, how many times does it cross the x-axis? None. Don't put 0, put none here. Okay? Is this a maximum or minimum? It is a minimum, so we don't worry about the maximum, right? It's a minimum, and the minimum value is at 3, because my vertex is at 0, 3. The direction of the opening is up. The range and the domain, so domain we know goes from negative infinity to infinity, and the lowest possible y value is 3, the highest possible is infinity. Round brackets and square brackets there. Okay, and that's pretty much what you're doing each time. Now the only difference here is that the form that we're given, they're going to give us different pieces. For 3, you can see they've given us all the pieces. So let's take a look at 2. So 2, if I rewrote that, my a would still be 1. This would be x minus 5 squared, and then my k value is 0. So my vertex here would be 5, 0. My axis of symmetry would go through x equals 5. My y-intercept here, what would that be? Well, if I'm putting the 0 in, right, so if I put in y is equal to 0 minus 5 squared, well, that would be 25, because 5 squared is 25. So this is opening up with a vertex at 5, 0. So let's put that in. Got 1, 2, 3, 4, 5. And then I would have my graph here, and it's crossing the axis here at 25, and it's opening up. So I can see here that my number of zeros is going to be 1. And it's going to be a minimum, not a maximum. It's going to be a minimum at 0. My y value is 0. Domain goes from negative infinity to infinity, and the range goes from 0 to infinity. Direction of the opening is up. Okay, so you can see it's much easier and much quicker than actually using your graphing calculator. All right, let's take a look at the last one here. They've given us all of the values. Y is equal to a x minus h squared plus k. My vertex is h and k. In this case, it would be 2 and 4. Axis of symmetry goes through x is equal to 2. The y-intercept's a little bit more work here. So y-intercept, we know we're setting x equal to 0. It's just more work because there's more math there, but still fine. 0 minus 2 squared plus 4. So it'll be minus 3 times negative 2 times negative 2 is 4. Remember bad math, you have to do your multiplication first. That would be negative 12 plus 4. So that our y-intercept would be equal to negative 8. So that's the only one that's actually hard to get your y-intercept out of, but everything else comes so nicely. It's actually not too bad because you're substituting in for 0. How many zeros in this case? Well, let's go ahead and graph this. So it's at 2, my vertex, and 4. My y-intercept's at negative 8. Down here. Now, as you can see, by putting in all those little tick marks, I'm actually assuming that these are the exact points where my zeros are. And I can't actually definitively say that. Okay, by saying that that's exactly where they are, that means I know what they are. But using the vertex form, you actually can't tell what the zeros are. I know that there's 2 zeros, so you got to be really careful when graphing. A better way to graph this, not that that's bad, but if I don't know exactly where the zeros are, I'm making an assumption there. So I can go back and put in just an estimate, negative 8, put in at 2 and 4. So I can say this is approximately 2 and this is approximately 4, right? And I could put that in at 2 and 4, and then I can graph this parabola like this, right? So that it goes through the vertex and it does that, but I'm not exactly saying where those zeros are. The more tick marks you have, the more precise you need to be when drawing your graph. So be very careful with that and be aware of what you're doing as you're doing. If you want to find those exact zeros, that's fine, but that's a lot more work than what we actually need to be doing in this question. Okay, my maximum is at the highest value of y, in this case is 4. There is no minimum. Domain from negative infinity to infinity, and the range goes from negative infinity to 4. And you can see that that maximum or minimum value are directly related to your range as well. All right, let's take a look at a different type of example. In example 2, it says determine the equation of a quadratic function given its graph. So very similarly to what we did with the factored form, but now we want to know what this would look like in vertex form. So I always start by writing out the vertex form and then plugging in what I know. Okay, I know that the vertex would give me my h and k value. Okay, in this case my vertex is at negative 1, 0, so that would be negative 1, 0, plugging that in, x minus a negative 1 plus 0. I could simplify that. Biggest mistake that students make, lose that squared sign. Do not lose that squared sign. Okay, that's very important for this equation. At this point, you feel like you're done because it looks like the quadratic function in vertex form, except you don't know what that a value is yet. And to find that a value, find any point along that curve to substitute. Now, any point will work, but I have told you in class that I always like using the y-intercept. Why? Because it has a 0 in it, and 0 is easy to substitute. So I'm going to choose the point 0, -2. Right? And you can see it right here. I've put a dot on it already. So substitute that in. Will any other point work? Sure. Find a nice one. Maybe you want to put in -1 and -8. Go ahead. You'll get the same a value as I do using 0 and -2. So it doesn't really matter. So plugging this in, I've got a y value of -2, x value of 0, and then I don't need to do that other 0 anymore. So -2 is equal to a times 1. So -2 is equal to our a value. Now we know our a value, so our function becomes y is equal to -2 x plus 1 squared. Now you're going to look at your graph and look at your equation and make sure that that makes sense. Well, I've got a negative a value. That's why it's facing down. Wonderful. I only have one root, or 1, 0, which is good as well. Here I've got it at -1, and -1 is there as well. So you can see that that fits. I always like to put a box around it when we're done so I can see where your answer is. Let's take a look at example 3. And this is the last example in the notes today. Solving a problem modeled by a quadratic function. So using what we know to figure out something that's a semi-real world situation. A soccer ball is kicked from the ground. After 2 seconds, the ball reaches its maximum height of 20 meters. It lands on the ground at 4 seconds. Determine the quadratic function that models the height of the kick. Determine any restrictions that must be placed on the domain and range of the function. What was the height of the ball at 1 second? When was the ball at the same height on the way down? Okay, well, we've got two variables here. We've got time and we've got height. And from previous examples and other experiences, you know that time is our independent variable, which will be our x, and height is our dependent variable, which will be our y. So if I look just as a sketch, right, this would be my time, x, and my height would be y. It says a soccer ball is kicked from the ground, so our starting point, fair to say, is at 0, 0, from the ground, and after 2 seconds the ball reaches its maximum height, and that lands on the ground at 4 seconds. So I can actually draw this curve knowing what's going on just from the description, because maximum height was at 2 seconds and the height was at 20 meters. And then the whole length of the trip of the ball was 4 seconds. And that makes sense, because if at the halfway point we're at 2 seconds, then all the way would be double that to give me 4 seconds. So I can actually generate the diagram right from there. Now it says determine the quadratic function that models the height. Okay, well, let's use our vertex form. Y is equal to ax minus h squared plus k. And in the vertex form, I can put in the 2 and the 20 as my h and k. So minus 2, oops, need the x in there, don't forget that. X minus 2 squared plus 20. Okay, is there anything else I can plug in there? Well, I can choose a point to substitute, right? If you chose 0, 0, that would work, right? Or if you wanted to choose 4, 0, that would work as well. You need to plug some point in the same way we did in this previous example. Choose a value to substitute. So why not choose 0, 0? In this case, so I put in 0 is equal to a, 0 minus 2 squared plus 20. And then I want to get rid of the 20 from this side. So I'm going to subtract 20 from here, subtract 20 from here. That's my 0 pair gone. So negative 20 is equal to 4a. Get the a by itself, opposite operation, divide both sides by 4. So I've got 1a is equal to negative 5. Which is wonderful, that's what I need. So my quadratic function becomes y is equal to negative 5 x minus 2 squared plus 20. And that's what we needed for A. Now for B, determine any restrictions that must be placed on the domain and range of the function. I'm going to just do that here. So the domain, in this case, specifically for this case, so in other cases where we're looking and you've got arrows, we know that the domain can go on forever, but in this specific example, the domain doesn't go on forever. Our x values start at 0 and end at 4. So those are the restrictions on that domain. For a range, the ball is going to start on the ground and reach a maximum height of 20 meters. So again, there's restrictions on that domain for this specific example. For C, what was the height of the ball at 1 second? Well, there's different ways of doing this. You can use substitution, right? You can use the graphing calculator and plug it in there. But what's important to recognize that time is x, right? So they're saying x is equal to 1 second. So if x is equal to 1 second, I can just plug that right in and solve it algebraically. So if I do that, y, I'm using my equation here, y is equal to -5. And then I've got 1 minus 2 squared plus 20. And you just plug this in and get your answer. So -1 squared plus 20, because I did 1 minus 2. -5 times +1. So y is equal to -5 plus 20, or 15. So what does that mean? That means a height of 15 meters. When the ball has been in the air for 1 second. Now you've got an option, same as you had for C. You could have done this with the graphing calculator or algebraically for D as well. It says, when was the ball at the same height on the way down? So if we look at our diagram here, I've drawn in a horizontal line at a height of 15. And you can see on the way up it's at 1 second. And what they're asking is how much time does it take for it to reach 15 again? I'm going to show it to you algebraically, but by all means, if you want to put this in your graphing calculator and just graph it, figure it out that way, then you can. This is just another tool that you can use. So looking at my equation, y is equal to -5 x minus 2 squared plus 20. That doesn't change. And you would think, well, if you're going to put 15 in, shouldn't you get the same value as you got before? Well, let's have a look. So height of 15, -5, I'm solving for x plus 20. So I'm going to do some algebra here. Get that x by itself. I got to move a lot of stuff around. Subtract 20 from both sides, so that goes away. So I'm left with -5 is equal to -5 x minus 2 squared. Get rid of the -5's here. That's fine. So I'm left with 1 is equal to x minus 2 squared. How do I get rid of that squared? Undoing that would be square rooting. So that cancels that. What's the square root of 1? Well, it's tempting to just put 1, but the square root of 1 is actually plus or minus 1. What is she talking about? Well, we know that 1 squared is 1, but we also know that -1 squared is 1. So when you undo that, we've never had to deal with that before. We always ever dealt with the positive answer and never really cared about the negative answer. But now we have to consider both values. Okay, so this is a whole new concept that the square root of a value can be positive or negative. Square root of 4, yep, positive or -2, not just +2. So we now have a whole bunch more solutions than what we thought before. I just put that one as an example. It has nothing to do with what we're doing. But just know that the square root of a value can be positive or negative, and often we dismiss the negative value, but we never even really talk about it. Now we have to find out, well, why do we need to talk about it? Because now you have two possible solutions. You can have +1 is equal to x minus 2, or you can have -1 is equal to x minus 2. Well, how does that change what we're doing? Well, if I rearrange and solve for x, add 2 to both sides, so that's 3 is equal to x. Hey, I didn't get that answer before. We're here, add 2 to both sides, 1 is equal to x. And that's the answer we got in part C, right? 1 second gave me a height of 15 meters. Well, guess what? 3 seconds will also give you a height of 15 meters. And if you want to go back and check by plugging that in, you'll get that. Do you want to see me do the check? Sure, why not? So y is equal to -5. Put in the 3 minus 2 squared plus 20. So 3 minus 2 is 1 squared, and that's where it is. Because when we put in the 1 there, 1 minus, right, positive 1 minus 2 gave you -1 squared. Well, -1 squared or +1 squared gives you the same answer. When you plug that in, -5 plus 20, hey, there it is. So graphically, it was easy to see because you could see there's that horizontal line that went through, and we understand now that that means on the way up it hits 15, on the way down it hits 15. But algebraically now you can see that that comes from the fact that when you square root a value, it can be positive or negative. Okay, so I've gone on a bit of a tangent, but I still answered the question, when was the ball at the same height? And the answer would be at 3 seconds. Okay. It's really important to understand this part D of example 3 because it's going to lead us right into the next lesson of using the quadratic formula and seeing that the square root of a value will give you both a positive answer and a negative answer. And sometimes we can dismiss that negative answer, but in quadratics often that's a really important solution for us. Thanks for joining me today.